So here's our starter today. We've got a person pulling on a rope at an angle here on a crate. Now the crate's not moving, it's pretty heavy, but I don't know, he's doing his best. And we just want to be able to handle problems like this. And here's how this is different than the problems we've done in the past. In the last unit, he would have been pulling on the rope horizontally, right? But here he is pulling on it at an angle. And what we need to know is we need to know how to handle that. So, and we're still going to use that 5-step procedure, but we're just going to add one little step to it. So we're going to draw a free body diagram of this crate. And then we're going to sum the forces in the x and y direction, and then we can talk about how we can actually use that to solve problems. But here's the crate. And obviously gravity is still pulling it down, m times g. We've got the floor pushing up on it with a normal force. Now, if he's pulling it to the right, but it's not moving, that means something has to be canceling that out. So we have a force of friction on here. And then, of course, we have this applied force. And at some angle theta. So that's what your free body diagram should look like. It should have these 1, 2, 3, 4 forces on it. Is that good? Did you get that far? Okay, then let's do step 3 though before we move on to B and C. Step 3 of the procedure says to identify your x and y direction. So we're just going to pick the standard x and y direction. But now we have to add a little step, a little part to step 3. And what was it? You got to break this force into its x and y components. You see, this guy is pulling the rope. That means that he's pulling up on the crate and pulling to the right. So he's pulling to the right and he's pulling up. Now, this makes a little right triangle, doesn't it? And we can express those x and y components using trigonometry. This is the applied force. Well, this must be the applied force times what? What is the adjacent leg of a right triangle equal to? The hypotenuse times cosine theta. And this is FA. What is the opposite leg? It's the hypotenuse, which is FA, times the sine of the angle. So now we can do part B and C. This was all A. But part B, well, I'm going to add all the forces in the x direction. They equal MA in the x direction. So I'll sum the forces in the x direction. There's 2 of them. There's the force of friction, but look at this. See, here's FA, but only part of FA is in the x direction. Only a component of it is this. And it's pulling to the right, which is positive x minus the force of friction equals 0. So this basically tells me, hey, this force right here is equal to the force of friction, which makes sense, doesn't it? But it's, in the previous unit where FA was horizontal, we would just say, oh, the force of friction will be equal to FA, and it's not. Now it's equal to FA times the cosine of the angle. Now we're going to sum the forces in the y direction. Equals ma in the y direction. This tells me what to do. First, I'm going to add up all the forces in the y direction. I come over here and I look at my free body diagram, and now I've got how many forces in the y direction? 3. 1, 2, 3. So let's add them up. We've got Fa sine theta in the positive y direction, because this guy is pulling up on the crate, plus the normal force, whoops, and then minus mg. And what's that all equal to? And why is it equal to 0? It's an equilibrium. There's no acceleration. Okay, now this is where we can stop. This is all I asked you to do. But notice that when we have a problem like this now, it's more complicated than what we did before, but we're really doing the same thing. For example, what if you need to find the force of friction? Well, we know that the force of friction is equal to mu, let's give it a mu in here, times the normal force, right? This is static mu. Well, you say, oh, if I need to find the force of friction here, and I want to express it in terms of the normal force, I got to find the normal force. Well, I can solve for the normal force over here, huh? But now the normal force is going to be equal to, let's add mg to the other side, and we'll subtract Fa sine theta from this. You all see how I got the normal force there? How I solved for the normal force? Now, here's something, this is really important. In the last unit, the normal force was on a crate problem like this was just equal to the weight, wasn't it? But now the normal force isn't supporting all the weight. Look, this guy is pulling up on the crate. The normal, so it's like he's trying to pick up the crate, right? So if he's trying to pick up the crate, then the normal force doesn't have to support all the weight. So we have gravity pulling down. This guy's pulling up, and if he's not pulling up hard enough, there's going to be a normal force supporting the rest of the weight. Doesn't that make sense? Okay. So here's all the weight. Something has to support it. Well, we got the normal force and the applied force, the y component of the applied force. So anyway, there you go. Now you could, if you know all this stuff, you can plug it in here, and then plug that in there, and then it's just algebra 1 solving for whatever happens to be the unknown, which I don't give you in this problem, but that's how you set up the problem. And the only difference between what we did then and what we're doing now is we're taking these forces and breaking them up into their components, their x and y components, and then including those components, those x components and the y components of a particular force in the equations for the x and y direction. That is all.